Text is everywhere. It's underpinning human civilization, and reading it has probably become second nature for you. Viewing text on the screen has become just as natural as seeing it in the real world. Not only is there a wealth of formatting options, the lines and curves remain crisp and readable at various sizes. But screens are made of pixels, so how's it done? Here's an idea. Do it like image files, just store the pixels each character consists of. This means it's really easy to draw, just copy and paste the pixels onto the screen. But raster images like these are very rigid. For one, you can't resize them very well. Making them smaller might look okay, but making them bigger is a great recipe for a blurry mess. You could work around this by just storing the images at higher resolution, just shoving more pixels in there, but then the size of your character data quickly gets out of hand. An image of just these 5 letters is already a considerable portion of the size of the real font I'm using for this example, and that one contains over 1,000 glyphs. Instead, how about we try to take inspiration from how humans write? A human wouldn't write this A by individually coloring in little squares. They'd simply draw 3 lines. Can we also do that here in Computerland? Yes, with the magic of vector graphics. Instead of storing the pixels, we can instead store the shape of this letter A, where its corners are and which dots to connect. And then fill in the pixels which would fall within the lines when we actually need it on screen. This way, we can reuse the same shape for any pixel size. We can even make pixels which are on the boundary various levels of gray to make it look smoother at smaller sizes. However, straight lines are not enough for most characters. For all of these wavy bits, we can use Bezier curves. These are a mathematical description of a specific kind of curve based on some extra control points. The font I'm using here is based on quadratic Beziers, so each curvy section is defined by its endpoints and one extra control point. See, the Bezier curve still goes from point A to point B, but how it gets there is influenced by where the blue control point C is. A single quadratic Bezier curve is very often not enough for complex shapes, like this S. Therefore, its contour is subdivided into small sections that can be better approximated by these curves. In fact, it's made up of 4 straight lines and 28 quadratic Beziers. If you need so many points to define letter shapes, how are fonts so space efficient in the first place? Well, storing lines and Bezier curves is just extremely light. Considering that defining a straight line needs only 2 pairs of numbers, 2 x's and y's, and a curve needs only 3, with a lot of repetition. This explains how a font file can be so small. An image needs to store data for every pixel, and you need a lot more pixels to get something coherent than the 92 points that make up this S. Saying A is cool and all, but unfortunately most words won't be made of just one letter. Even if you could communicate with only single letter words, it's not like we can even draw multiple words at once right now. The main problem here is that after we put this Y on the screen, we don't know where the next character should go. Ostensibly, it should be somewhere to the right, but where exactly? To alleviate this, with each character, let's store how much horizontal space it takes up. After placing a letter, start placing the next one that distance to the right. We can repeat this process to put together a whole word. Because we can give characters arbitrary amounts of space, we can even have, well, spaces. Just leave the graphics empty, but still make it take space. Hold on, that doesn't look right. Here we have some characters which are taller than normal, like this uppercase Y and this lowercase d, and we're centering them vertically individually. Clearly, we should be aligning by their bottom edge. Oh, some characters, like this lowercase y here, should descend a bit below all the others. Since aligning by the graphic doesn't work by itself, we also need to store where each character is positioned vertically and adjust the alignment using that information. This imaginary line, which every character sits on, is called the baseline. We can now write a line of text. It's very plain text, but still text. Unfortunately, an approach this simple doesn't quite cover all the gaps. Consider the combination AV, where our current solution seems to have gone a little overboard on the spacing. But for a different combination, like AB, it looks fine. What gives? Well, notice that the A extends to the right near its bottom, but the V extends to the left near its top. There isn't much horizontal space between the rightmost point of the A and the leftmost point of the V, but because these are at very different vertical positions, there's always quite a bit of distance between the letters' edges, causing this unsightly gap. To fix this, we'd need to move the V to the left a little, depending on which character comes before it. This process is called kerning, after kerns. The overhangs used to achieve this in metal type blocks. For this purpose, fonts will also need to contain information about which pairs of characters to apply this correction for, and how much adjustment is necessary. How well does our current approach stack up for other languages? For everything written with the Latin alphabet or its variations, it will work just fine. In this example, we just have to add a couple extra letters with diacritics on them. But that's pretty much the limit with our system. There are languages like Arabic which are written right to left, and some languages can even be written vertically, like Japanese. Well, writing top to bottom actually isn't that hard, just move downwards instead of to the right after each character. However, putting Arabic text on screen turns out to be much more difficult. For one, what shape a character is depends on where it is in the text. To achieve this, several additional font features are required, which unfortunately would take way too long to explain here. Also, these are the exact same digit characters you're used to, and, in fact, they're written left to right, unlike the rest of the text here. Why, you may ask? Well, a consistent ordering ensures that numbers won't get mangled when switching text directions. And historically, they were laid out this way. Because of the direction mixing, the layout here requires the Unicode bidirectional algorithm, which is quite expansive. But the gist of it is, first split up the text into runs with the same text direction. Note that the text in each run is always stored logically, in the order it is read. Then, lay out those runs in the context's text direction, which is right to left in this case. Real text renderers can also apply a lot of different formatting options. They can change the color, make it bold, italic, add an underline, cross it out, and even mix fonts and sizes. Currently, what we have here can do none of that. How are all of these effects achieved in practice? Well, making text colorful is quite simple. Recall that the font only specifies the shape, so just fill the pixels in a different color. Adding underlines and strike-through is mostly just drawing some extra lines. Bold and italic variants are also fairly simple. They could be created automatically with some code manipulating the vector graphics, but in practice they're just different versions of the same font, since font designers will want to have complete control over their shapes. For example, in some fonts, the lowercase a completely changes its shape once italicized. Hold on, how do we even mix different fonts in the first place? Well, by the baseline, of course. A particular font might have smaller or larger descenders, the parts that go below the baseline, like in the letter P. The lowercase letters may vary in height, etc., but aligning by the baseline means everything will stay roughly aligned, and thus easy to read. Similarly, we can mix different sizes by also aligning the baselines. Writing on a line is great, until you run out of space. Unfortunately, screens aren't infinite, so sometimes we've got to go down as well. But how? You can't just split text all willy-nilly. Breaking words down the middle would be incredibly awkward. So, instead, some characters are designated as preferred places to wrap lines, most notably spaces. Text is written to the right until a character doesn't fit, then go back to the last break boundary and start over from there. If there is no break boundary on a line, then as a last resort, break in the middle of a word. This still allows for text alignment options. After laying out the whole line, usually some space will be left over, which has to go somewhere. Put it all on the right or left, for left and right alignment respectively. Split it in half and put it on both sides for center alignment, or distribute it along all of the line's spaces for justification. There are also cases where the layout has to constrain itself around the text. In this example, the text on the right influences how much space the bars get. The percentage labels are also aligned by the right edges, so they influence each other. Or even something as simple as a button. Its size is the size of the label plus some padding. Thanks for watching. While this video may seem like it's quite in-depth, in reality this is only the surface. For one, I glossed over rasterization, how the vector-based character contours get turned into pixels. There are several neat tricks and techniques used in this process, especially useful at smaller sizes. In the upcoming weeks I will make a series of short-form videos explaining some of them. There are also a lot of interesting font features which I'd like to cover in the future, such as ligatures, variable fonts, or colors.